And now let's continue with the Chapter 5.3 Heat Transfer Part 2 on convections and radiation. So now in here, let's take a look at convection. Convections of heat in liquid and gas. So as we mentioned before, liquid and gas are not a good conductor. But in here, let's take a look at it. How can it be conducted some other way other than conduction, as in our last video? Which process are we calling that? We're doing that in terms of convection. So let's take a look, what does it mean by convection? Now, in here, the convection of heat in liquid or a gas. Let's take a look at the video first to show you what it looks like. Okay, so it's getting a little bit slower. Give it a second.
Part A. Convection of heat in water. Set up the apparatus as shown. Convection tube, alcohol lamp. Add water to the convection tube until it is almost full. Add a few drops of food colouring to the convection tube, which gives the water red colour. Light the alcohol lamp and then heat the water on the left bottom corner of the tube. Observe the movement of the coloured water. Part B. Convection of heat in air. Set up the apparatus as shown. T-shaped cardboard, candle. Place a glowing splint as shown. Observe the movement of the smoke. How do the hot air and cold air flow in the beaker?
Okay, so in here, our first experiment is on the convections in liquid. So if you take a look at the liquid, you see that when the Bunsen burner is heating up the liquid on one side, the clear liquid actually is pushing away the food coloring and will go around in a circle. So in here, the water is being heated, and when the energy is applied to the cold water, it turns it into hot water. And in here, as our last chapter, chapter 6, we mentioned that the hot water actually has a lower density. So it means that it's lighter. You want to go up. So what happened to the empty space that the hot water left behind is replaced with the cold water because it's denser, it's heavier. So it will replace the space that was left behind by the hot water. So you can see that it will go around in a circle, in a loop. And that's the first part of the experiment. And then in the second part, so if you take a look at this experiment, the candle are being lighted. And the reason why we have a stick that is burning is to generate the smoke. In here, if you can see the smoke, actually you can observe that the smoke is being transferred from one side of the stick all the way to the candle. The reason for that is the candle will actually be heating up the air above it. So the air is being heated, so it will be lighter, it will escape the beaker. So what happened to the empty space left behind? The air from the other side with the smoke will be replacing it. So you will see that the cold air actually will replace the hot air next to the candle. So in here you will see a convection current happening. So let's take a look at the PowerPoint and to consolidate what you have seen here. So in here, let's take a look in this setup. And in this setting, you might see this experiment again in Form 3, and it's a good experiment to see how the convection current happens. And in here, sometimes you will see a potassium permanganate to be replaced with the coloring. Sometimes people like to use that, but that one is poisonous, so you have to be careful about that. I'm pretty sure your teacher will warn you about that if they use that. Now in here, that's the setup. So let's take a look at what will happen again. The lighted or the hot water will rise up. So it will go up and around the tubes, and then it will touch on the coloring and it will just go back down because it starts to cool down, and then it will go to the other side. And that's why you see this cycle of going up around it and coming down, because it starts to cool down. And we call this a convection current, because it's like a current, it will just go around and around. So in here, let's take a look at the answer. The colored water moves to the right, and will it rise or sink? It will sink towards the bottom. Okay, then it moves to the left because it's replacing the one that has gone already, and will start to rise towards the top part of the tube. So you have to see that in your diagram. The water are being moved around in a circle, and then as it cools down, it will be replaced with the hot water, and it just go around. Hot water turns into cool water, and then it just keep on going in this circle. In the second experiment, we have the candle and with the T-shaped cardboard. The reason for that cardboard is to separate the cold air from the hot air. So in front of the cardboard there with the candle, the air will be really hot and will want to escape from the beaker. And in here, the glowing sprit is at the back, so that whatever cold air will be coming from that side, or from your left hand side, going around it, the bottom, and come out of it. So let's take a look. In here, the movement will look like this. The hot air next to the candle would go up because hot air has a lower density, it want to go up. And the space left behind, the void, what would happen to that space? Is replaced with the glowing sprit's cold air. The glowing sprit only produces smoke. It had only a slight temperature change, so we consider negligible in the room temperature. Only the candle with the really high temperature, with the burning, that will generate a lot of energy. So in here, you see that there's a U-turn from going down and then going back upward. So it's from the left hand side going around it and going to the right and then going on top. It's like a tunneling effect, and it will go up that way. So in here, how do the hot air and cold air flow in the beaker? The hot air above the candle flame rises because of the lower density and draws the smoke to move with it. So in here, the cold air will replace the space left behind by the hot air. Once you understand this concept, how is the heat transfer in water and air. So the first one we use the water, the second one with the cardboard is with the air. So in here, when the water or air is flowing from below, the hot water or air rises at the same time. So basically the hot one will go up, doesn't matter it's water or air, and we have got a name for that, is we call that a fluid. Water or air can be considered a fluid. The cold air or water sinks to replace the one left behind. So basically the really hot one, the higher temperature will go up, and the lower temperature will come back down to replace it. So that's why there is a replacement, and we give it a name of a current, convection current. So please copy this down. And in here, we give the liquid and air and the gas a name. We call that a fluid. So in here, if you are interested in engineering, there's a subject called fluid dynamics. That is a tough course. If you want to study anything with the air movement, the aerodynamics of airplanes and so on, fluid dynamics is essential to know. So in here, you just consider water or gas are considered to be the same material properties as a fluid. Now, in here, that's a summary of what we learned in the experiment. So in here, as the hot water rises, it will turn around, and then it would start to come back down from there. And the animation stops, unfortunately. Now, so in here, you see that it will cool down on the other side, and then it becomes cold water. And of course, if you just keep on going around and around, the hot water will just keep on rising in temperature, and then the cold water will not be that cold anymore. The temperature will start to rise as well. So the overall here, you will see a movement of hot air or hot water rises, and then the relatively cold water sinks to the bottom and replaces the void that is created by the hot water here. Now, in here you see that there is a convection current. You see that is the in dotted green lines here. The current is going around and around. So the idea of current is it would be a closed loop. It's like a circle. It will go starting from somewhere, it will go around it to some places and come back to the starting point. And we consider it a current. Okay? And next, we got the hot air rises from next to the candle. We're considering the case of gas. What will happen is the cold air would comes back down. You have to think of it as in 3D. The hot air is not only going in here, one can draw 2D, but actually in the 3D environment, if all the air around the candle are being hot and being heated up and then turn it back down in a looks like a circle. So in here, all the air around the candle are being heated up, and the air next to it are being cooled and going back underneath it to raise the hot air space. So in here, convection requires a medium to transfer heat, either a gas or liquid. Okay, in here there's a little bit more. I need to show you that. Give me a second to go back out of this page. Okay, so in here, we need to see that it looks like in here. However, convection only takes place in liquid or gas. It cannot take place in solid. So in here, there's the idea of convection does not take place in solid. The reason for that is because the solid, water particles are locked in. It cannot move anywhere else. In here, only liquid and gas would allow the particles to move around a little bit more. So that's why in here, solid does not work. Only gas and liquid works for convections. So in here, let's take a look at our key point. So in here it's obvious we are talking about convection. Convection is the transfer of heat from one place to another by movement of liquid or gas. So in here we give the name fluid for liquid or gas. This kind of heat transfer cannot take place in solids. So in solids it would not work at all. So you have to be aware of that. Now, in here, the application of the effect of convection. So how do we apply it? First of all, we look at the electrical appliances of, you see, it doesn't work. So I have to show you this way. Now in here, so you see that in here, the convection current, as we mentioned before, the heating plate is at the bottom. So the heat will be transferred to the liquid, to the water, and heat it up this way. And then in the middle, the heat will go up. Once it reaches the top, it will come back down because it will start to cool down a little bit. And then come back down and then keep on going in this cycle. And we call that convection current. So you see that it will go around like that. And after that, we have an example of the air conditioner. So in here you see that the reason why we put the air conditioner at the top is because the cold air will sink to the bottom. And then when the hot air will be rising, and then it will be next to the air conditioning and replacing the cold air that's left behind. So it will just keep on going to have this kind of currents going around and around the room, so the whole room can be cooled down. And next, in Hong Kong, we can observe this. In a hot summer day, you will see that you can actually feel that if you're standing next to the ocean, you will sense a ocean breeze, or here is sea breeze, because during the day the land is heating up a lot faster, and then the heat will be going up, and then the space left behind will be replaced with the wind coming in inland, so from the ocean to the land, so we can sense the sea breeze. At night it will be the other way around. All the heat from the ocean actually would be a lot higher than the land. So the ocean would be actually rising up the heat, and the cold air from the land would be coming out of it. So in here you see that for the first case, the sea breeze, a lot more heat absorbed in the land. So you see the temperature there in the land is higher, much higher than the ocean. The ocean would not give that kind of temperature rise. And if the temperature rises a lot faster in the ocean, humankind would be in a big trouble. A lot of ice melt and other things with global warming, as you are aware of it. So in here, the land absorbs more heat. So that's why the hot air rises, and then is created an empty space left behind by the hot air. And the ocean air is actually cooler, so that you can sense the sea breeze. The direction is from the ocean, blowing the wind to the land. So you can actually feel that the cold air coming into the land. And that's why you feel a little bit more comfortable if you stand next to the ocean. You can sense the sea breeze because of the lower temperature of the wind coming in. Now at night it will be an opposite direction. The reason for that is because the land would dissipate the heat. The heat will go a lot faster, go away faster than the ocean. The ocean retain the heat longer, so it keeps the heat longer. So you compare the temperature, you see that the land actually generates a little bit less lower temperature than the sea, and from that the opposite direction of the current happens. Hot air rises from the ocean, not the land this time, and then the cold air will be blowing from the land outward. So in here, that's why if you're standing next to the ocean, you will feel that the wind actually goes in the opposite direction as you normally would expect it during the daytime. The nighttime, the breeze will be going from the land to the ocean. Now, in here, let's take a look. We complete the table here and give a second to think about it. So we know that conduction is good for solid. We know that it's really good. So what happened to the convection? Can it happen for solids? Give a second. We mentioned that just a couple minutes ago. And how about liquid? For conduction, does it happen at all? Is it a poor or good? Think about it. The liquid for conduction, and then the liquid for convection. Does it happen in convections? And the last case is the gas. Give a second, think about it. What do you predict? Which one will be better? Which one is good? Which one is not possible for sure, as we have mentioned that in this video. Okay, so let's take a look. So in here, only solid in convection cannot happen, not possible at all, because all the particles are locked. You cannot break it, and we have a name for that lock. We call that a bonding, but you don't know what that is yet. You will learn that in chemistry in Form 3. But now you can think of it, it's not possible for them to move, so that in convection the solid is not possible. And for the convection, liquid and gas are good at it. That's why you see the smiling face in E and F. But for B and C, it's really poor. It's poor in conduction. Doesn't mean it does not happen at all. It just means that they are poor at it, that's all. But it still happens. Really, really slow, that's all. Okay? And after that, we come to the idea of radiation. Radiation actually is an interesting topic because it happens in vacuum. Some of you realize this with the next example we have here. And in here, vacuum is an interesting idea because vacuum means that there's nothing in there. But actually, that's not the case. With the modern physics, we know that even in vacuum, there's something called dark matters. What that is, we do not know. Even the physicists right now, all the scientists around the world, we are trying to make that, but we do not know what that is. But we can prove with the math we have, all the detection we got around the world, is that for every particle, every one of you, the person, there are 5 times as material of dark matters behind it. So you can think of it this way. So you are sitting and watching this video at home. There are 5 of you in terms of material. Where that is, we do not know. But in math, we can prove that. So it's up to you to find out what is dark matters. And of course, it's advanced physics. You will not find that in the textbook in high school. But it's a good topic to look into if you're interested in. And if you understand that, you can let me know because I'm trying to understand it myself. Okay, so now let's stick with the textbook, with the heat transfer by radiation. Now in here, we mentioned the verb vacuum here. So in here, from the sun to the earth, there's nothing in between that. We call it vacuum. And yet, there's something called dark matter that is really strange. And people don't know what that is, and we're still trying to understand what that is at this point. But right now, just assume vacuum is vacuum, nothing there. So the radiation would come from the sun all the way to earth, traveling in vacuum. So in here you see that there's nothing there, but the heat, you can still feel the sun. If you don't believe me, just go outdoor tomorrow and look at the sun. Well, not look at the sun. Feel the sun. The heat is on the skin. You can feel the heat. How does it get to your skin? It's by radiation. It's an interesting idea. Nothing there and it still works. How does it work? Not sure. But there's some properties we can understand. For example, if you are standing next to the electric heater, you can feel warm. The main process of heat transfer is radiation. We are not talking about convection currents as in our last part of the video, but we know that it's moving to you in different directions. We are not talking about if you're putting your hands on top of the heater. We are saying that you're standing next to it and the heat somehow can get to you. And there's the EM wave, but that's a little bit above your level of understanding at this point, so I will leave that out. Now in here, the heat can be transferred through a vacuum by radiation. So in here, we just want to introduce you to the idea of radiation. And there are some experiments we can do. Absorptions and emissions of radiation. We understand some of the properties by radiation. We can understand it through this experiment. So in here, all objects absorb radiation. That's important for you to know. Some of them are poor, but they still can absorb. Everything absorb radiation. So what kind of surface would give you different ways, and how does it work actually? Let's take a look. So in here, I will show you a video on the experiment. And this experiment, I would suppose you will see it again in Form 3. So let's take a look at it first. Okay, give it a second.
A dull black flask A and a shiny silver flask B are provided. Fill the flasks with the same amount of water. Set up the apparatus as shown. The distance from the light bulb to 2 flasks are the same. Record the initial water temperatures in the 2 flasks. Turn on the bulb. Record the final temperatures after 10 minutes.
Okay, so in here, we're comparing 2 different flasks. Let's take a look at A and B here. So in here, there's one word you need to learn, doubt. It means boring as well, but in here, it means that the surface itself, you can see that it's not as shiny as the B. Doubt is opposite to shiny. And also the color, black versus the silvery. Okay, so in here you can see that the silvery is different from the black, and then the doubt is different from the shiny. Okay, so what does this 2 tell you? There's something to do with the way it absorbs the radiation by looking at this. We turn on the light bulb and we measure the temperature. You see the 2 probes that is being put inside the flask A and flask B there is connected to a computer, and we call that a data locker. And it will just record all the numbers there and put it into a graph. So you can tell that one line is higher, one line is lower. Guess which line is higher, A or B in here? In this case, compare A or B. You're not sure? The answer is actually mentioned in the video. See? You see flask A, the doubt and black one. actually start off with higher temperature already compared to the line below it. The bolded line A is the one with dull and black surface. Fast B is the silvery, shiny silvery. So you see which one absorbs more energy, absorbs more radiation. As it shows you in this graph here. So you can tell that the dull and dark surface absorb more energy. So that's why you see the line goes higher than the other line. Now let's go back to the PowerPoint. Okay, so let's take a look at the procedure here. So in here, we're comparing two things, the finishing and the color. Dull versus silvery versus shiny, black versus the silvery. So in here, there's the setup with the same distance. The reason for that is for a fair test again, and we want to control we want this to be a control experiment, and we want it to be a fair test between A and B. Okay, so in here we record the initial temperatures. Unfortunately, we don't have the actual experiment to show you, but what we can tell you is, this one I need to show you one more line. In here, which flask A or B shows a larger rise in water temperature? Is A. Is the dull and black. It absorbs more energy. In here, you need to know the answer. It's A. Before we move on to the discussion. This one. So in here, how does the color affect the way of the absorption of radiation? Dull, black surface absorb radiation or heat more steadily than silvery, shiny silvery surface. So in here you see that black and dull are actually good absorber of radiation, so it absorbs more. So that's why in the winter time you would prefer to wear a dark jacket, and people like to wear that because it will absorb more heat. And in here, I need to hurry up a little bit. I can't show you the polar bear. If you're interested in seeing why the polar bear actually is black, that's the reason. They want to absorb more heat. How come the fur is actually looks like white? You have to look at the Form 3 video that I talk about it a little more. But we are running out of time in Form 1's video, so we have to go on. Now, in here, you see that dull and black surface are good absorber of radiation. Shiny and silvery actually is a poor absorber. And in here, so you see during the summertime, you prefer to wear something white or light color so that it will absorb less heat. And in the winter, you wear the darker jacket to absorb more heat from radiations. And in here, that's why it's a good absorber of radiation, while the other one is a poor absorber of radiation. And in here, all objects also emit, meaning giving out radiations. We were talking about absorption, so they will absorb the heat, they will take in more heat. But right now, we're talking about giving out heat, emitting radiation. So in here, there's a experiment to show you. It's a similar setting as what we have in here, 5.9, but it's 5.10. Okay, so you see the setting looks similar. But this time, let's take a look.
A dull black flask A and a shiny silver flask B are provided. Fill the flasks with the same amount of hot water. Set up the apparatus as shown. Record the initial water temperatures in the two flasks. Record the final temperatures after 10 minutes.
Okay, so it's similar to what we have set up in the last experiment. We got two flasks, A and B. Same thing again. A is the dull black surface, so the finishing is a bit rougher on A. B is shiny and silvery. And we put the hot water in there for it to dissipate the heat, to give out the heat. And we connect that to the data locker. So in here, it's important to see which line represents the flask A. So in here, so take a look at the beginning. At the beginning here, flask A actually start off with a lower temperature already. Remember, flask A is the one with the dull and black surface. And actually, it start off with a lower temperature already. It's the moment you put in the hot water, it start to give out the heat already. So in here, even though we start off the same temperature with A and B, they would actually be seeing the difference at the very beginning already, because it's giving out a lot more heat, emitting heat. Use the word emit, so it's faster to spell. So in here, after 10 minutes, you see that the line below actually will remain lower than the silvery lines on the top. So in here, A actually will be dissipating the heat more, emitting the heat more, full radiation, giving out more heat. So in here, you will need to know that the dull and black surface actually is a good emitter, also a good absorber of radiation. It happens to be both of them go at the same time. You're good at one thing, you're also good at the other thing. So in here, that's the setting. And from that, we don't have the answer for this one, but we can conclude from that. Oh, I need to show you the other part first, which is on here. So in here, which flask will show a smaller drop in water temperature is flask B, with the silvery one. The reason for that is it will give away less heat. So in here, in the discussion, how does the color of surface affect the emission of radiation? The dull and black surface emits radiation more than the silvery the shiny silvery surface. So in here, the dark black surface actually is a good emitter, so it gives out more heat. At the same time, it is taking in more heat in the last experiment we have done, but in this experiment, it also shows that it will give out heat easier than the silvery one. So in here, it's concluded that it's a good absorber of radiation, also a good emitter of radiation. So it's good at both. It's good at absorbing and good at giving out the heat, full radiation. Now, in here, we conclude that dull and black surface are good emitter, while silvery surface are poor. So it's easier for you to remember. So dark and black surface are good at everything, good at absorbing and good at emitting. Both of them are good at it at the same time. Okay? So how do we apply it to our daily life? We look at the refrigerator for sure. If you take a look at your refrigerator, at the back of it actually have a lot of lines like that, and they usually print it black. That's the reason, because you want to give out more heat. You wouldn't put it under the sun. You want to cool down your refrigerator. And in here, all those lines are for the heat to dissipate faster, to give out more heat easier. And that's why we call it the radiator. That's the reason for that, because it will give out the radiation. So we give it a name as a radiator. Now, in here, all the cooking utensils, they are silvery and shiny, right? So in here, actually, it will keep the whatever heat is inside longer. You never think of this way, but the shiny surface actually help the heat to remain inside the pot longer. And in checkpoint 5.6, we have the heat can be transferred in air by radiation. Is it true or false? Heat can be transferred in air by radiation. It's true. Actually, you don't even need the air. The heat will still be transferred because actually the radiation does not require any medium at all. Of course, if you have air, they would do it, but you don't really need to have that. In the second part, the silvery, shiny silver surface absorbs more radiation than a dull black surface. Is it true or false? Think about the last experiment we have. Does the dark black surface give out more heat? In here, you see the false, because it will actually in here, the more should be changed to less, because it will give out more heat for the silvery surface. And we got one more question here of the vacuum flask. And in here, it talks about convection, convection, and radiation at the same time. So let's take a look. So we got a stopper at top, we got vacuum, we got the silvery surface inside, and let's take a look. So the stopper, what does it stop? If we have really hot liquid inside, which convection, or radiation does it stop? It stops the convection. Okay, and in the next one, the stopper is made of plastic. They're poor conductor of heat. It prevents heat loss through conduction. So it doesn't touching it, it does not give out the heat away that easily. And the last one, the silvery glass wall prevents the heat transfer through radiation. Because it's silvery, the radiation doesn't like that, so it would want to stop it with the radiation. And the last one, the vacuum between the wall prevents the heat transfer through conduction and convection. So in here, the walls actually, it has vacuum, so it's not touching anything. There's empty space there, and the conduction needs to be touching something, and convection needs a medium, needs air, solid, something. Not solid. The air or liquid, but it doesn't have anything there. That's why convection will be stopped. And it comes to the end of this section on chapter 5.3.